All right, welcome back. That actually worked out much better than I thought it would. I'm sort of stealing a Khan Academy style here on the black background, but my name is Mr. Dybel, and I'll be working out problems. Who knows? I'll start with 11 and see where we get to, and I'll put it in the title whenever I figure out what I go to. So I'll be working problems out of my Semester 2 final review, and on part 1 we did 1 through 10, which was about converting to and from rational exponents. But here on number 11, we're going to be simplifying radical expressions. Now this has shown up on practice sheets time and time and time and time and time again, and I still get questions from students as like, how do you do this? How do you do this? How do you do this? Every time I need to keep explaining. So this will be serving as a good explanation for all of you who still don't know how to do it, which is fine. So number 11 is, actually I don't know if I like that color. Let's do something brighter. So number 11 is the fourth root of x to the third, y to the 10th, z to the 12th. So what you want to do here is you want to treat this as separate things, right? You want to take the fourth root of x to the third, the fourth root of y to the 10th, and the fourth root of z to the 12th. Once you get the hang of these, this won't be necessary, but I'm just doing it for now. Now, you want to think of this as, like, you want to try to break what you've got inside here into multiple pieces. So we'll leave the x to the third for last because it can't be simplified. But we'll start with the z to the 12th, right? Imagine z to the 12th as four groups, excuse me, three groups. Four is not good. So, like, if you guys can agree probably that z to the 11th times z to the first is z to the 12th, right? Well, or z to the 10th times z to the second is also z to the 12th, because what you're doing is you're adding the exponents together, right? When you're multiplying a common base, you add the exponents together. So what we want to do is utilize the fact that the fourth root of something, in this case z to the fourth, we want to utilize the fact that the fourth root of z to the fourth is just z. Because as we were learning earlier, that would be to the 4 over 4 power, which is z to the first. Right, so we want to utilize this here. So what we want to do is we want to rewrite z to the 12th in chunks of z to the fourths. So if I had z to the fourth, then what would be left would be z to the 8th, because 8 plus 4 is 12. So I could write this, and I'll go ahead and do this over here, as like z to the fourth times z to the 8th. But z to the 8th again could be written as z to the fourth times z to the fourth. So we'd have 3 z to the fourths. Right? And if you added all these powers up for a 12, you get z to the 12th. And that's what we're looking for. And that doesn't look like a 12, but I promise you, it is a 12. This is just my handwriting. So what we want to do is consider this as the fourth root of z to the fourth, z to the fourth, z to the fourth. And just like we split this piece up into separate chunks, you can split this into separate chunks. You can consider this as the fourth root of z to the fourth times the fourth root of z to the fourth times the fourth root of z to the fourth. And like we were saying, the fourth root of z to the fourth is just z. So that would be z times z, which is z cubed. Right? So really, simplifying the fourth root of z to the 12th, it all simplifies into z to the third. Now, a simpler way to think about this, sort of like a shortcut version in your head, right? This is all of the math behind it, but a simple idea is that if you can afford to subtract away like this number from this number, so if you take 4 away from 12, every time you can do that, it pulls a z out of the radical. So you can afford to take 4 away from 12, so you would pull 1z out of the radical. Then you'd be left with 8. Then you can take 4 out of that, and you'd pull a z out again, and that leaves you with 4. And then you can take 4 out of that, leaving with none. So when you take the last 4 out, there's 3 z's outside of a radical, which gives you z cubed. Right? That's sort of like the shortcut method, and that's what we'll be using from now on. Right? But it comes from all of this. Right? So you've got this piece simplified as just z to the third. Now the y to the 11th, or the y to the 10th power, right? This piece, if you take 4 away from 10, you're left with 6. So when we do that, one of our y's comes out of the radical. All right? Then you still have 6 left, so you can afford to subtract 4 again, and you have 2 remaining under the radical here. And you've got another y pulled out. Now you can't take away 4 from 2, so you leave it under the radical. So that would be y squared times the 4th root of y squared. So that's this piece simplified into that. So we've got these two pieces. And then here, notice you can't take away 4 from 3. So you can't simplify this down anymore. Now, in certain circumstances, like imagine the 4 was a 2, right? If you had the 4th root of x, or the 3 was a 2, you had the 4th root of x squared, right? Well, if you converted this to a rational exponent as x to the 2/4, that could simplify to x to the 1/2, but we're not really getting into that right at this second. And I go off on tangents a lot. If any of you are not my students somehow and you manage to find this link, hi, but I sort of go off on tangents. I apologize for that. It's just going to keep happening, so you're going to have to learn to deal with it. So we've got the whole problem boils down to this, an amount of terms outside of the 4th root, and then an amount of terms inside the 4th root. So under the 4th root, we'll have x to the 3rd. We'll have y to the 2nd. And then no amount of z's are left under there. And then outside of the root, we've got y to the 2nd, right here, and a z to the 3rd. So that is your simplified answer. All this culminated into this one part. Now, that is number 11 worked out, and now we need to move on to number 12. Number 12, and I'm going to try to conserve some space here, because I don't know how quickly I could get more space. So number 12 is the square root of 81 x to the 9th y to the 14th. And if you can't read my handwriting, I do apologize, but you should have an actual hard copy of this review, and you know what number 12 is. You've got the printed copy. So here, again, you want to think of this as the square root of 81, the square root of x to the 9th, and the square root of y to the 14th. Now, on the 4th root, we had a 4 up here. We're like, okay, well that's great. You can take 4 away as we were doing here. You're like, well, there's not a number here. What am I supposed to do? Well, we call it a square root for a reason. There's really like a 2 out there, right? So the square root of 81 is just simply 9. And then, again, you want to go through this process of removing 2, like subtracting it away. So how many 2's could you afford to subtract away from 9? Well, you could take 4 sets of 2 away from 9. So you would have 4 sets, which would give you an x, an x, an x, an x. So an x, an x, an x, an x. And then under your square root, you would still have 1 remaining. So once you take away 8, you now have 1 left, and that will stay under. Now for the y to the 14th, you could take away 7 sets of 2 here. So 1, 2, 3, 4, 5, 6, 7. And then you would have none left, because when you subtract 14, you get 0. So the idea here is when you simplify, you're going to get 9, and then there's 4 x's, so x to the 3rd, and then there's 7 y's, so y to the 7th, times the square root of x. And that's it. Moving on to number 13, we've got the cube root of the following: 27 x to the 6th, y to the 12th, z to the 3rd. All right? So again, consider this all separately. Cube root of 27. Well, that's 3. And then the cube root of x to the 6th. You can afford to take 6 away. All right? So take 3 away, and you'll have x squared on the outside. And then here, look, 3 does go into 12. It goes into it 4 times with no remainder. And so you've got y to the 4th out here with none on the inside still. And then you can take away 3 from 3 just a single time, leaving you with z to the 1st. And you've got no radical over here. So that's your simplified answer. Number 14. I think number 14 is the last one we'll do in this part. This finishes up this little section. I think I might do these section by section. Number 14 is the 5th root of the following: x to the 14th, y to the 10th, z to the 21st. Now this is, like I mentioned it up here, but thinking of multiplying and remainders and division is good when you're talking about simplifying radicals like this. So how many times does 5 go into 14? Well, 3. No, 2. So it's x to the 2nd, right? That would give you 10. And then it would have a remainder of 4. So in the 5th root will still be x to the 4th. And then here, 5 goes into 10 twice, exactly, with no remainder. So it'd be y to the 2nd. And then here, on the z, 5 goes into 21 4 times. So you've got z to the 4th. And you have 1 left over. So you have z to the 1st. So there is your number 14. All right, hopefully this has been helpful, and we will pick up on number 15 on the next part, and we'll work all the way through number 20 on part 3. Thank you for joining me. Hopefully you stick around for the next part.